Hello all. Today's topic is regarding the type 1 hypervisor. So till now we have discussed with respect to the first video, which is data center on wheels, and the second video, which is hypervisor. So now in this video we will take a deep dive into the type 1 hypervisor, which is basically what will be used in our HPC inside the STP vehicle. Okay. So with this, let's get started. So this is how our general traditional system behaves. So you have an application in the user space, and it needs some access of some disk or whatever in the physical hardware. So it does a syscall from the user space to the kernel space, and kernel space basically speaks to the hardware, and it returns back whatever is needed. Okay. So this is how it generally works. Now, in the hypervisor system, so you have the user space. A syscall is made from user space to the kernel space of the guest operating system, which is actually running inside a virtual machine. Okay. Now, when this particular operation happens, the hardware, the actual CPU hardware intercepts this particular call, and it diverts it to the hypervisor via a hypercall or a privileged operation. Okay. And from there the access to hardware or whatever is needed is done, and from there the same thing is sent back to the user space. So this particular hypercall or privileged operation is what which will be an extra layer over here. Okay. Now uh, previously we have discussed with respect to architecture. Now we'll go a level deep. Okay. So as we already discussed, we have a physical hardware over here, and we have a type 1 hypervisor. So type 1 hypervisor could be anything like Zen hypervisor, Hyper-V, or whatever it is. And then you have various virtual machines running on top of this particular hypervisor. And as I said earlier, the communication from the kernel of the operating system, of the guest operating system, to the particular hypervisor could be via the hypercalls or via the CPU trapping the instructions to hypervisor. So these are the two methods using which this thing happens. Okay. And as we previously discussed, the hypervisor will be in the ring -1. Okay. Now the job of this hypervisor is not just to intercept these requests, but also to make sure that each of this VM is allocated the CPU resources, is allocated the corresponding memory, and it has the virtual drives, virtual devices, and which basically speaks to the actual physical devices, and as well as creation of virtual communication uh, channels between multiple virtual machines. Okay. So the hypervisor basically creates virtual CPU cores and allocates them to the corresponding virtual machines as per its requirement. And similarly, in memory management, it uses the extended page table or nested page table, and from there it actually manages the memory. So what actually happens is, you have a virtual machine which is basically running in the kernel space. Sorry, in the you have a application which is running in the user space of the virtual machine, and this will have a corresponding page table with respect to the memory allocation. Okay. So it will have a memory address, and it will basically have a page table pointing to the physical addresses which it thinks of the guest kernel, which is basically running in the virtual machine. But in reality, it is the physical memory is not over here, it is over here. Okay. So you will have another layer of mapping over here. So say the address space is 100, and which is basically mapped to 200 over here, which it thinks is the physical memory, but it is not. This particular 200 will be mapped to another memory location of 300, which is basically maintained by this hypervisor, which in turn is mapped to the hardware, the physical hardware. So that's why you have the extended page table or nested page tables over here. Similarly, and these are bit deeper topics. I would suggest, like if at all you guys are interested, you can do your own search with respect to the virtual CPUs and the extended page table and nested page tables out there, and you will get the information. So it will become a bit lengthy. That's why I'm not discussing in this video too much. And we have the IO for this particular virtualization, as we discussed earlier. So for every virtual physical device, there will be a virtual emulation which will be basically done by this virtual machines, because the guest operating system has no idea that it is being virtualized. And we have the virtual bridge, okay, between the multiple virtual machines which are running. Now say we have to do a inter VM communication. So we will have the application. We basically use the sockets. On socket you can basically have any protocol which you want, like gRPC, TCP, some IP or whatever it is. So this is treated as one machine, this is treated as another machine, and the communication happens the usual way. But the thing over here is there is no physical connection over here, because both of them are on the same PC. So the data will be moved from will be on the same machine only, but it will be moving at the memory level only, not via any connections and all, because both of these are on the same machine. So there is no movement of data over wires or whatever. It is only at the memory level. Okay. Now the interesting part, because, and another thing is, like, as this is only the standard protocols like TCP or whatever, it will have an IP address, it will have a port number. Similarly, this will have an IP address, some port number. So you do a REST call, or you will do whatever communication you want over this port numbers only. Okay. And as these protocols are OS agnostic, we will not have a problem at all. Okay. So say you have a use case where you need to transfer huge amount of data, but you need not have any multiple copies of it. Say the image data or some LiDAR data, point cloud data, or whatever it is. In that case, how do? You need to use a shared memory. Okay. Now this is where the tricky part will come. You are so generally how shared memory works is, you have one process which is maybe creating the shared memory, I mean, like, which is creating, which is getting some data, and it is dumping at a location. And you have another process, or you can have multiple processes which are basically accessing the data from the same memory location. Instead of making a copy of it, basically what happens is, the process A, which is basically dumping the data into the memory, is locking the memory location, dumping the data, unlocks it via mutex or whatever. Okay. And there is the process B, which basically locks the location, accesses the data, and then unlocks it. So there is a mutex based operation or semaphore based operation which makes sure that there is the data is safely handled. Okay. Now this is possible because both of these processes are running on the same operating system. Okay. And they will be using the same kind of mutex lock unlock. Okay. Now think about a situation. You have a virtual machine which is a QNX based for SLD applications, and you have another virtual machine which is basically on Linux, which is handling the non-critical applications out there. Okay. And as we have seen earlier, the actual physical memory stays in the physical layer only. The VMs don't have like, they feel that they have the physical memory, but in reality they don't. Okay. Now in that case, how does the mutex operations or semaphore operations happen with respect to a memory location where the operating systems are different altogether? Like the way the multi-threading or the safe memory access for QNX is different with respect to Linux. So how do you do it? Okay, now this is where the hypervisor provides you a CPU level instructions, which is not dependent on OS, which is OS agnostic. Okay, so using that CPU level instructions, the QNX can basically lock a region while it is dumping data, and the Linux system can also lock the region while it is trying to access the data out. Okay, so previously we didn't have this particular problem because we are speaking over a protocol, and the protocol is same irrespective of what operating system you are running on. But that is not the case when it comes to shared memory. Okay, that is where the hypervisor provides you the CPU level abstractions, CPU level instructions, so that you can basically handle these kinds of edge cases also, the uh, IPC mechanisms like message queues, shared memory, etc. Okay, so this is one of the what to say core feature, I would say. Okay, now there is something called as para virtualization, and I will tell you, explain you the difference between a full virtualization and a para virtualization. Okay, so if we go back in a full virtualized, so this particular block diagram architecture which I drew is with respect to a fully virtualized system. Okay, so there we have a virtual hardware, and we basically have the virtual network interface cards, we have virtual disk and other things. Okay, because the virtual machine, the operating system running inside the virtual machine thinks that it is not virtualized, it is running on a physical machine. Okay, because of which we have to do an emulation whenever it tries to access the disk, or whenever it tries to access any other physical hardware. A layer of emulation is happening, which is once that is done, the instruction is intercepted by hypervisor, it routes it to the physical hardware, then it gets the output. From there it is sent back to this particular virtualized hardware. So this emulation is happening. Okay, now this is happening because the operating system as such is used directly without modifying it and saying that, buddy, you are basically a virtual guy, you are not running on a physical machine, and you don't have any access directly to the physical machines. That is something which this particular operating system doesn't know. So that is called as fully virtualized system. So that is where para virtualized systems comes in. Okay, where what happens is, in a para virtualized systems, in a para virtualized hypervisor, the hypervisor stays the same. It is still the type 1 hypervisor only, but the operating system which is running on top of it is para virtualized. Okay, so here basically we modify the operating system such a way that the operating system knows that it is running on a virtualized environment and it doesn't have any physical hardware or physical drivers. So you can basically try to access the physical drivers directly without any emulation through the hypervisor. That is the modification in the guest operating system which will be done. Okay, now so as I said, so the guest awareness, so here the guest VM is not aware that it is virtualized, but here it knows that it is virtualized. Similarly, the device emulation, it is done in the fully virtualized system, but it is not here in para virtualized system, because the guest OS knows that it is anyways not a physical machine. Okay, because of this emulation overhead, the performance is lower in a fully virtualized system. But in a para virtualized system, as there is no emulation at all, the performance with respect to the operations is quite high with respect to accessing the physical drivers and physical data flow and other things. Okay, now the compatibility means like any operating system can directly be run on top of a fully virtualized system, because you are directly taking the operating system as such. But in a paravirtualized system, that will not work because you have to customize the operating system for your own requirement. Okay. But in a typical data center use cases, they really are not working on a safety critical system. So for them, you specifically need not do any para virtualization, and you need not kind of put effort on top of it. It is not that much needed for them. So, and it provides them a lot of flexibility because you don't have to customize any operating system for your own need. Okay. But that is not the case for a para virtualized system because we are using it for use cases like ours in SDV, HPC, where you basically are dealing with real time systems and speed is everything. Okay. So it comes with its own drawbacks. So in a para virtualized system, the guest operating system modifications are needed, and it is needed as per your own requirement. So when you customize something for your own requirement, basically you're on your own. No one will maintain the burden. The burden will be maintained by you. Say some issues happen. Now those issues should be basically fixed by you only if at all something happens. And say you move from one operating system to another operating system, or in that same operating system only another version and all, the portability will not be so smooth. So these are some of the issues with respect to para virtualization. Okay. Now in the previous video, I discussed like, what is it up to, like how things will move forward. Okay. So here we are talking about a hardware where the hypervisor, because the existing hypervisors out there, they they are not SLD qualified. So you have to basically create a hypervisor which is SLD qualified, and on top of it you have to create the operating systems so that which is para virtualized, because we for our use case speed is everything. So we are okay with respect to modifying the operating system for our own requirement. Okay. And maintaining it as per the hardware and all. So this is where typically in a automotive use case, when you had 100 to 150 ECUs and all, where there was no HPC and all, these things were not so complicated. You had lot of tier 1 suppliers and other players who were actively uh, involved in this particular creation of the boards and all, where they had the expertise and other things. So you the typical, the legacy tier 1 suppliers like say Conti, Denso, Bosch, all these companies. Okay. But when the systems are becoming sophisticated, this is where the actual semiconductor players, they are jumping into this particular game. Like Nvidia, Qualcomm and all. Nvidia has its own drive hardware, which basically tries to provide the user with this kind of hardware so that you qualify the hypervisor for SLD, and you run the operating systems on top of it, where the operating systems are also optimized with respect to the hardware so that speed is everything. Okay. So in my previous video, I think some 2 years back or so, where I told that this particular transition is happening, like new players are entering into the game. So this is the reason why they are entering the game, because this is their expertise, this is their area where they are good at, and they are trying to what to say, create create a proprietary hardware ecosystem so that the things are efficient, and they control the solution as much as possible. Okay. So this is the end of the type 1 hypervisor, and I hope by going through the data center on wheels video and the hypervisor video and this current video of type 1 hypervisor, you might have got a good idea with respect to why this particular hypervisors are so crucial for SDV with respect to HPC, and what are its own, I mean, like what are the sophisticated uh, problems which are being solved for bringing this HPC to reality. Okay. Thank you all. Thanks for your time.